Almost everybody, whether you live in a small rural village or a large urban metropolis, has access to the entirety of human knowledge through a small device like this in their pocket. That is an insane feat. But only 100 years ago in the 1920s, radios were just coming to the homes of the American citizen. They ran anywhere from $40 to $100, which in today's currency is almost $1,000 for a radio. So how did we go from $1,000 radios to a $10 single board computer with over 1,000 times the processing speed of those devices back in the day? Well, you can thank this rock for the technological explosion that's happened over the last 100 years. And not specifically this rock, but the element that's found commonly in this rock, silicon. But before we talk about the technology that silicon created, we have to discuss the technology that silicon replaced. In the 1950s, there were computers, but they weren't the same as the ones we have today. Computers in the 50s were all controlled by vacuum tubes. As the name implied, a vacuum tube was a glass tube that contained a vacuum on the inside that would control the flow of electricity through a heated plate. By heating an electrically charged plate, referred to as a cathode, inside of the tube, the electrons on the plate would undergo thermonic emission to the anode on the other side. To control how many electrons went across this gap in the vacuum, a control grid was put in the middle that would control how much electricity went across the gap. For the sake of electronics, being able to control the flow of electricity with electricity is fundamental to create logic circuits. Even in the early 1940s, data was stored as a series of ones or zeros, electrical voltages that say that the voltage is either on or off. Logic gates are a way to do logical operations on whether or not two signals are on and off. For example, an AND logic gate will be positive if both ends of the AND gate are on. Or another example is the NOR gate, the opposite of OR. If one or the other is on, then the result is zero. Using these logic gates together, you're able to create circuits that represent human logic and the foundations of computer programming. By combining one or more vacuum tubes, you're able to create logic like the NOR gate, the not OR gate, or the NAND gate, the not AND gate. By combining the NOR gate and the NAND gate together, you can effectively create the logic for any circuit. Now, vacuum tubes, as the name implied, contained a vacuum and only worked under those conditions. Because they were made out of glass and required heat, hence thermonic emission, they were extremely bulky and impossible to maintain. If the glass broke on the vacuum tube, for example, the vacuum tube no longer transferred the electrons and you no longer could have the logical property of the vacuum tube. As the circuit grows in complexity, the circuit also physically grows in the size that it occupies because of how large vacuum tubes were. This made any vacuum tube logic circuit very heavy and power hungry. Because of this, these devices were extremely expensive and hard to move around. For example, this circuit here, which is huge, power hungry, and expensive, is a flip-flop circuit used to contain a single bit of information. So how did we go from a single bit being this size to billions of bits being this size and sitting in my pocket? This is where silicon comes in. Silicon is classified as a semiconductor. A semiconductor lives in the gray area between conductors and insulators. A conductor, for example, like copper, that easily transmits electricity, it conducts electricity, and glass, which is an insulator that conducts no electricity. A semiconductor will or will not conduct electricity based on some variance in its physical properties, such as the material's temperature. Now, a semiconductor on its own is not very useful. The conductivity of a semiconductor is not predictable or exploitable in a way that is useful to electronics engineering. To make a semiconductor more useful, one must change the electrical properties of the semiconductor to make it more useful for electronics engineering. In the early 1940s, the patent was released for the ability to turn a semiconductor into a more useful material, referred to as doping. To dope the silicon and make it more useful, the silicon atoms were blasted with atoms that are either more negative or more positively charged than the silicon. By doing this, you're able to create two types of semiconductors that could be used in electronics. By doping the silicon with a more negatively charged atom, you create a donor or an N-type semiconductor, or by doping it with a more positive atom, you create an acceptor or a P-type semiconductor. N and P-type semiconductors on their own are both equally pretty boring. But when you put them together, this is where the magic begins to happen. By putting a P and an N-type semiconductor together, you create what is called a P-N junction. The p-n junction is the foundation of all electronics in the modern era and is the foundation of the diode and transistor electronic components. Where the p and the n semiconductors meet, a barrier is created. The p side has holes for electrons and the n side has free electrons to give. By putting these two together, you create a barrier where electricity can only flow in one direction. This on its own is the diode. Now this is where silicon comes to life, and it's awesome. If we then take two p-n junctions and make an n-p-n or a p-n-p device, we create a device with three fields. We have a collector, an emitter, and a base. By applying a voltage at the base, we're able to control how much current flows from the emitter to the collector. And what does that mean? What have we done? We have created a device that doesn't use vacuum tubes, that is able to control the flow of electricity from one part of a circuit to another. We have created a device that will replace the vacuum tube that has no vacuums and no heat required. This device, known as the transistor, heralded the electronics revolution of the 1950s and 60s. Transistors went about and replaced every vacuum tube in modern electronics and shrunk the size of machines that used to occupy entire rooms down to circuits that could fit in the palm of your hand. The first transistor was invented in 1947 by scientists Brattain, Shockley, and Bardeen at Bell Labs in Homedale, New Jersey. Interestingly enough, the first transistor they invented actually didn't use silicon at all. It used germanium, which is an element that was thought to be more easy to find and easier to produce and cheaper than silicon. The problem with germanium was two things. One, germanium actually ended up being more rare than silicon as mining technology advanced in the 1950s, but also germanium broke down at 80 degrees Celsius chemically, which meant that as the transistor was used in amplification settings, the germanium would actually melt in those transistors. In 1958, Jack Kilby and Robert Noyce took these transistors and turned them into ICs, or integrated circuits, that allowed you to compute extremely complicated digital logic in a chip that's about the size of your finger. This also made electronics more reliable by reducing the amount of parts in a system that could break and reducing all of the logic to a single chip. If that chip went bad, you buy that same chip and replace it, as opposed to having to have an inventory of thousands of different capacitors and resistors that each could break individually. Integrated circuits in the 1950s and 60s were extremely expensive because they were hard to produce. But as time went on, new methods of manufacturing allowed for these devices to become cheaper and cheaper to produce in bulk. Methods like photolithography that use light to create patterns of transistors on silicon wafers, as well as atomic deposition that allow manufacturers to produce very specific layers of chemicals to create ICs in mass. Also, these processes have made it easier for transistors to get smaller and smaller, therefore reducing the size of electric devices. For example, Taiwanese Semiconductor Manufacturing Company, or TSMC, has plans to produce a 2 nanometer transistor in 2025. 2 nanometers is an insanely small size. So small that you're actually getting to the point where you have issues in the realm of quantum physics about how the electrons are behaving inside of the transistor. Despite these issues, the transistor has brought significant change to the world, upgrading us from the early days of vacuum tube technology to the day where I literally have access to anything I want to know in my front pocket. We could not have gotten here without transistors, and we could not have gotten transistors without the rock that changed the world, silicon. If you like this video, hit subscribe, and we'll see you in the next one.